I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on some rotational motion, starting with angular kinematics. In this series of videos, we're going to talk about rotational motion, torque, and angular momentum, so objects rolling or rotating. Up to this point, we've talked about things moving generally in a straight line with the exception of centripetal motion, but that was when an object was moving at a constant speed, moving in a circular path. In this unit, we're going to talk about things speeding up and slowing down. We're going to start with rotational motion and angular kinematics. So let's start with the types of motion. The motion we're familiar with is called translational motion, and that's a motion in which all of the mass moves in the same direction. So for example, a box sliding down a ramp. Now we also have, in this unit, we're going to talk about rotational or angular motion. And that means an object is rotating about an axis. All particles that are on that axis or on the disk rotate around the axis, but not all particles are moving at the same speed. So for example, a disk, and it has two coins sitting on it. And those two coins are a distance from the center of the axis, different distances. And as that object rotates, we can see that both of those objects do not move at the same speed. The black coin is further out, so it's moving a further distance. And the red coin is closer in, so it moves a shorter distance in the same time, which means the black coin is going to move faster than the red coin. So let's look at the comparison of the kinematic variables. So we have rotational or angular kinematic variables and translational equivalents. So angular displacement, that is just the angle in which something is rotating. And the symbol is the Greek letter theta. So one revolution around is 2 pi radians, and that is the unit of measure for angular displacement is radians. Arc length is the translational equivalent when something's rotating, and that's the distance traveled around a circular path. The symbol is S and measured in meters. So if you think of the circumference, it's 2 pi times r. That's a rotation one time around a circle. The arc length is the circumference, or if it's a little bit shorter, that's the symbol is for measuring the arc length of a path that something has rotated. Angular velocity is the rate at which the object rotates. The symbol is the Greek letter omega, and it is the rate at which the radians are changing. So it's the measurement is radians per second. The equivalent we're used to is we've seen speed. Speed is the rate of a moving object. The symbol is v, and that's measured in meters per second. Now we also have angular acceleration. The angular acceleration is the rate of a rotating object's velocity changing. The symbol is the Greek letter alpha. So this is the rate of an object rotating. As it rotates, it speeds up in terms of its speed spinning, or it slows down. That would be the angular acceleration. Now we also have to take into account the centripetal acceleration. Something has a centripetal acceleration when it's rotating, so we would combine those two. And the angular acceleration is measured in radians per second squared. We also have the acceleration, which is the rate at which velocity changes. The symbol is lowercase a, and that's measured in meters per second squared. So why should we have angular variables? We already have these kinematic variables. Well, because all objects rotating have different speeds because they of the different radii. So if we look at our coins rotating again, and we look at the path that the black coin takes, and we look at the path that the red coin takes, we can look and see that the circumference, the inner circumference of the two of those, and let's take those off of this circular path and translate those into a straight line path, so unroll them, and we can see that the arc length of the black coin is much longer than the arc length of the red coin. So we know that S of the black coin is greater than S of the red coin. So the farther the object is away, the greater the distance traveled. So both objects take the same amount of time to rotate, therefore we know that the one further is from the center is moving faster. However, both objects made one full revolution, which is 2 pi radians, so they have the same angular displacement. And because they have the same angular displacement and they moved, rotated in the same amount of time, they're also going to have the same angular velocity. So the reason we have angular variables is even though things are moving at different speeds in terms of translation variables, We know that the angular variable values are going to be identical whether they have the same radius or not. So let's look at the connections between the kinematic variables, starting with rotational converting to translational. So if we take the rotational angular displacement and we multiply by the radius, that's going to give us the arc length, much like taking 2 pi radians 1 rotation times r gives us the circumference. The angular velocity is the change in angular displacement per time, so it's the rate at which the radians are changing. And the symbol angular velocity times the radius, that's going to equal our tangential velocity, the subscript t representing tangential for the speed. So that's our tangential speed is angular velocity times the radius. The angular acceleration is the rate at which the angular velocity is changing. So that's speeding up or slowing down of a rotating object. It could be a disk, it could be a bike tire, something along those lines, that some circular object rotating. Take the angular acceleration times the radius, that's going to give us our tangential acceleration. So this is only part of the acceleration, as we mentioned before. Something rotating also has a centripetal acceleration. The centripetal acceleration combined with the tangential acceleration is the overall acceleration. So to sum that up, we've got each of our angular variables. If you multiply an angular variable by the radius, it gives you that translational value, whether it's arc length, tangential velocity, or tangential acceleration. There's one conversion that you may need to use at some point, and one of the units of measure is revolutions per minute. So this is a common unit of measure for rotating gears inside a car engine. You may have a tachometer in your car that shows the revolutions per minute of the gears in your car. But the standard unit of measure is radians per second, and that's what we're going to use in our kinematics. So to convert 1 revolution per minute, we're going to use something called the factor label method, where we're going to multiply by equivalent of 1, 2 pi radians per 1 revolution, their equivalent values. Revolutions would cancel out. So now I have radians per minute. So to convert minutes to seconds, I multiply by 1 minute over 60 seconds. The minutes cancel out. And that gives me pi over 30 radians per second. So 1 revolution per minute is equivalent to pi over 30 radians per second. So I can take RPM, multiply by pi over 30, and that would give me radians per second. And vice versa, I can multiply by 30 over pi to go from radians per second back to revolutions per minute. So let's look at the kinematic equations. So we have the translational kinematics, the first 3 kinematic equations on your formula sheet, the first 3 equations on our formula sheet. So you can see here's the angular equivalent to that first kinematic equation, where all we've done is we've changed the v's to omegas and the a to alpha, and time is not an angular measurement. So time stays as t. If we look at the second kinematic equation, we can see all we've done is we've changed the x's to thetas, the v's to omegas, and the a's to alphas. And you can see how easily it would be to derive the from translational to angular. The first 2 kinematic equations are on your formula sheet, the angular kinematic equations, but the third one is not, but you can see it's going to be easy to derive using the third kinematic equation. Just change the v's to omegas, a's to alphas, and the x's to thetas. As of 2024, the AP Physics 1 formula sheet does not have that equation. So let's look at an example problem using angular kinematics. So we've got a bicycle rider uniformly accelerates from rest to 9 meters per second in 30 seconds. Each tire has a radius of 0.4 meters, and we want to know the angular acceleration of the tires. The only thing we know is the radius. So we know a kinematic variable in terms of the initial velocity, final velocity, and time. So the first thing we're going to do is we're going to find the tangential acceleration using translational kinematics. And there's 2 ways you can do that. One is by using the list of variables that we looked at one of our first videos this year, is using the kinematic equations. And you can click on the link above to check that video out. Or you can use a velocity time graph to find the velocity using the velocity time graph. We know that clicking on the link above would help you review looking at velocity time graphs. So if we're going to use the kinematic equations, which I'm going to use both, we list all our variables, we fill in everything we know, we cross out the one thing we don't need and don't have, we put a question mark next to acceleration because that's what we're looking for. And then we know that we're going to use that first kinematic equation because the first dash is not used. Then we could also draw a velocity time graph and see that our final velocity is 9 meters per second in 30 seconds. If we're going to use the kinematic equations, cross out anything that's zero, rearrange and solve for acceleration. Velocity over time is going to also represent the slope of this graph. So slope being the acceleration on a velocity time graph, we can plug in velocity over time, and that gives us 0.3 meters per second squared. But that's not the question. The question is angular acceleration. So we have the tangential acceleration of 0.3 meters per second squared, and we can use this equation that alpha times r equals the tangential acceleration. We can rearrange that, solve for alpha, so the tangential acceleration divided by the radius is going to give us the angular acceleration, which is 0.75 radians per second squared. So let's look at the second part. So how many rotations do the bicycle tires undergo while accelerating? So number of rotations, that means we're going to have to use angular variables. So we can list all of our angular variables just like we do in our kinematic variables, just changing x's to thetas and omegas, v's to omegas, and alpha replaces a, putting the dashes. And then we're going to convert all of our variables from translational to tangential. And we can see the 9 meters per second divided by 0.4 meters. Once we've converted, then we can fill in our list, or we can create a velocity time graph. In this example, I'm going to do both. So we can see that we know every variable but what we're looking for, the angular displacement. So we can find the angular displacement either using the angular velocity versus time graph by finding the area underneath that graph, or we know that we can use either the second or third kinematic equation. So in this case, we chose the second because it's already solved for angular displacement. Cross out anything that's zero, simplify that, and now we have theta equals 1/2 alpha t squared. Or we can use that triangle, use the 1/2 base times height, or substituting in for the theta equation, 1/2 0.75 times 30 squared, and either equation is going to give us 337.5 radians. However, it didn't ask for radians, it asked for how many rotations. So we have the number of radians. We're going to convert radians to number of rotations. So one rotation, remember, is 2 pi radians. The way I remember that is the circumference of a circle, 2 pi r, divided by r, that's going to give you the number of radians. Remember, the angular displacement is going to equal the arc length divided by the radius. So we're going to take 337.5 radians, multiply by one rotation over 2 pi radians. The radians cancel out, and that's going to end up giving us 53.71 rotations. So the bike tires rotate 53.71 times. So the next question is, what distance did the cyclist travel on the bicycle? Now we can answer this question in multiple ways. We could use kinematic equations, the translational kinematic variables, but we know how to do that already. We could also draw a velocity versus time graph, but we've done that already. So let's see what we can do to find the distance by just converting our angular displacement to the distance the bicycle traveled. Remember, angular displacement times radius equals the arc length. In this case, the arc length is also the distance that the bike travels. So all I have to do is take the number of radians and multiply by the radius of the bike tires, and that's going to give me the distance that the bike travels, which is 135 meters during that 30 seconds, speeding up from rest to 9 meters per second. So this was an introduction to angular kinematics. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at Cavi Coaches.